am Sarihasa of rule number 55. Today we're going to discuss the following topics: pipelining introduction to pipeline, general pipeline structure and diagram, and arithmetic pipeline. Now, pipelining. What is pipelining? Pipelining is the decomposing sequential process into sub-operations, with each sub-process being executed in segment, currently with all segments. What does that mean? That means that we are going to take a process that operates sequentially in an order, and we are going to divide it into sub-operations. And these sub-operations we are going to execute in individual segments, and all the segments are executed concurrently, at the same time. Now, what is the purpose? The purpose of this pipelining is to keep the processor occupied. That is to utilize the maximum efficiency of the processor. We use this pipelining. Now, what are the types of pipelines? There is arithmetic pipeline, there's instruction pipeline, and it's also reduced instruction set computer pipeline. But today we're going to discuss about arithmetic pipeline. But before that, let's look at the general structure of the pipeline. The general structure of the pipeline consists of a clock and an input, and the R1, R2 that you're looking there are the registers, and they are used to store the results in each step so that we can keep a track of our own. And the time space diagram. Now, generally when we're using computers, the T1, T2, T3, T4, T5, T6, all these instructions, they are executed after that. Like in the first clock cycle for the instruction, T1, T2, T3, T4, T5 are there, and after T6 the next T1 starts. But if you're using pipelining, after the execution of T1 itself, during the execution of T2 itself, parallelly T1, that is the second instruction T1, will also be executing. This really saves a lot of time for the processor and also uses its maximum efficiency. Next, we're going to discuss arithmetic pipeline. Now, what is arithmetic pipeline? Arithmetic pipeline divides an arithmetic problem into various subproblems for execution in pipeline segments, as I said regarding the arithmetic pipeline. Now, what is arithmetic pipeline? This is used for floating point operations, multiplications, and various operations. Now, floating point operations are those that are conducted on floating point numbers that we will be looking in the future time. Now, this arithmetic pipeline, as we are looking at, consists of 4 sub-operations. What are these? Those are comparing the exponents, aligning the mantisas, fixed point addition, and normalization of the result. Now, as we go forward, we are going to look at the 4 different operations. We are taking 2 floating point numbers, 0.9124 into 10 power 3 and 0.9257 into 10 power 4. These are the 2 floating point numbers that we are taking for the current example for the demonstration. Now, the mantisas are the decimal part of the given number. What is the decimal part? 0.9124, and for the second number it's 0.9257. Now, what are the exponents? A is equal to 3 and B is equal to 4. Exponents are the ones for the 10 power. What is that? That is called as the exponent. And for the second, next we're going to perform the first step, that is comparison of the exponents. Now, among the 2 numbers that we have read before, what are the exponents given? A is equal to 3 and B is equal to 4. Now, from this we have found that B has the larger exponent, and then we have to find out the difference of the 2 and store it. What is the difference? I have used modulo here, so mod 3 minus 4 is 1. Now, for the second step, we're going to align the mantisas. Why? What is aligning? Aligning means that whatever the number is there with the smaller exponent, the number with the smaller exponent, it is not number, sorry, shift the number with the smaller number to right. That means what are you going to do? You're going to take the number, and the number that has the less exponent value, that is, in this case it is a has value 3, so that is less than 4, so a has the lesser exponent value, so we are going to shift the number by t units. How many units did we get for the t value? We've got the t value as 1, right? So we're going to shift the a number by 1 unit. That after shifting we get the a value as 0.09124. And for the third step, we're going to perform the fixed point addition of the two fractions to produce an intermediate sum. Now this is not the final sum because it's not normalized yet. It is just the intermediate sum, and the intermediate sum is the sum of the two decimal parts. Now what is it? 0.09124 plus 0.9257. Now after adding these two, we're going to get 1.0104394. Now this will be the intermediate sum. The process is not completed yet. This is the intermediate sum, and in the last step we're going to normalize the result. Now this normalization means that after point itself all the digits should be there, before it nothing should be there. So for this the process will be find the number of leading zeros, and for the given intermediate sum, for the sum, and shift the result that we got in the third step by u units. So we're going to find the number of leading zeros, which in this case is -1, and we're going to shift c, the number given, by those -1 units. So if we shift c by -1 units, we're going to get this value, that is 0.104394 into 10 power 5, because after shifting we have to also increase the exponent value by by t units. Okay, so we are also changing the exponent value, and these are the 4 operations that we are going to conduct, and this is the flow diagram for the floating point addition. Now I'm going to explain this diagram. This diagram consists of 2 parts, exponent part and mantissa part. And exponents part, I'm going to take the example here. So here the exponents, what did we get? They are 3, and I apologize for that. The exponents are 3 and 4, and the mantissas that we have obtained are 0.9142 and 0.9257. Now what are we going to do? We are going to store these exponents in a register for the first step. This belongs to the segment 1. In this we are going to do the saving into the register, so we can use it for later purpose. In the segment 1 we are going to compare the exponents, that is the operation, the one that we have read before, by subtraction. So 3 minus 4 will be getting 1 as the answer in the segment 1, and that we have stored in a register. And we're also going to find the difference. What is the difference? The difference that we found, that is 1. And here after comparison, here we store the larger value. I apologize for that. Here we store the larger value of the two opponents, that is between 3 and 4. 4 is the larger one, so we're going to store 4 here, and then we're going to take the smaller one. We store the smaller one, the smaller exponent we're going to store here, that is 3 value. And as for the difference, we're going to take the difference 3 minus 4, that is 1, and we're going to store the difference, and we're going to use this difference to align the mantissas as we have read in the second step. Now after aligning the mantises, whatever the result we get, we store that in this register, and after storing this register, we perform the addition part, that is in the third step. We perform the addition part, and after performing the addition, the intermediate result is stored here. This happens in the segment 3. After that, we need to normalize the result. How do we normalize the result? By finding the number with the smaller exponent, and we're going to normalize the result, right? So for that, we're going to take the result, and using the number of leading zeros, we're going to adjust the exponent, and now we are going to store the end result in this register. Now this is the flow chart to perform the floating point addition or subtraction. It depends on your requirement, and this is the way of present. This is the flow diagram of arithmetic pipeline, and with this the arithmetic pipeline topic is done. Thank you for listening to me. Have a great day, everyone.